Hello, everyone. Today I will present my reading and summary for my paper, The Reliable Multicast Framework for Lightweight Session and Application Layer Framing. The paper is published in 1995, and the authors are listed here. This paper describes a scalable, reliable multicast, SRM. It is a reliable multicast framework for application-level framing and lightweight sessions. The algorithms of this framework are efficient, robust, and scale well to both very large networks and very large sessions. I will introduce this paper from these 5 aspects. The first one is the background of reliable multicast. So the reliability is one of the most general requirements from applications. Generally, there are 2 types of to achieve this reliability. The first one is the sender side reliable. For example, a sender waits for the acknowledgement packets from the receiver and retransmit the original packets if the timer expires. This is commonly used in the unicast. And another type is the receiver reliable. This is the type when the receiver sets up this timer and the receiver sends the not acknowledged packets NACK on loss detection or the timer expires. And the requirements for the reliability moves to the multicast scenario. It's very hard to achieve because first, applications have different requirements on the delivery. For example, some applications require that the delivery obey a total ordering, while many others do not. And some applications have many or all the members sending data, while others only have one data source. This is the second aspect. The number of sources are different because in multicast, there are a group of members in the same group, and each one of them could be a source of the data delivery. So the number of sources are different. Unlike the unicast where it's end-to-end communication, there's only one sender and one receiver at the same time. And number 3, the third reason makes multicast a reliable delivery is that the multiple receivers causes more message exchanges. For example, some applications have replicated data, for example, in an unredundant file store. So several members are capable of transmitting a data item, while for others, all data originates at a single source. And also, if we use the same strategy as we just introduced, the sender reliable or the receiver reliable delivery, and there will be lots of ACK packets transmitting from the sender and the sources, and the sources and the receivers. So in this way, the message exchanges very frequently with lots of duplicated packets in the network. Here, this is a graph to describe the sender reliable strategy in multicast. First one is that the sender waits for the ACKs from all receivers and resend on timeout or selective ACK. Second, per receiver state in sender should be recorded as the sender size. So in this way, it's not scalable. And third, this causes the ACK implosion. Here, let me give you an example to show how this sender reliable multicast works. So first, the sender sends out this 4 packets, sends out 1 packet, and each packet will be delivered to R1, R2, R3, and R4 respectively. And for each packet designated to R1 to R4, they will set up a timer for each packet, and once the receiver receives these packets, it will send back the ACK message to tell the sender that I have received these packets and you don't have please send the next one. However, if, for example, if R3 did not receive this packet, it will not send back this ACK, and the ACK timer at the sender side, specifically for the R3, will be expired, and so the sender will need to send another packet only for R3, or if in this in a multicast fashion, it will be sent out to all these R1, R2, R3, R4 again until all of the ACK packets, ACK messages are received by the sender side. In this way, the ACK implosion is caused. And also, remember, we have to set up a timer for every sender, every receiver, and so it's not very scalable. Another strategy is the receiver side reliable. Three features are listed here. First one is the receiver sends the NACK resend request to the lost packets. Second, it does not provide 100% reliability. Third, it may cause the NACK implosion. Let me give you an example to show how the receiver side reliable multicast works. However, if one packet is lost, for example, in this figure, the packet 1 is lost, then all of the receivers, they will send, when the timer expires, they will send this NACK message to the sender, as shown in this figure here. So you can see the network will be flooded with the NACK message, and the sender will learn that most of them did not receive the packets, the packet number 1, and this is caused this causes the NACK implosion. So here we have provide this ideal multicast retransmission strategy. So first, the packet 1 reaches R1, but is lost before reaching other receivers. This means like the R1 successfully received these packets. However, when the link between these two routers broke and the rest of the receivers, R2, R3, and R4, failed to receive packet number 1. And in this case, only one receiver sends the NACK to the nearest sender or the receiver who has this packet. For example, the R2 first detect this packet loss, and because the timer set up in itself before the packet arrives. So it sends out this CK message to the multicast group, and the receiver number 3, receiver number 4 will all be receiving these packets. And in this case, the repair packets is sent only to those that need the packet. So this is the most ideal multicast retransmission, which will not cause duplicated packets in the whole network. Next, let's move on to the design principles of scalable reliable multicast, SRM. So the scalable reliable multicast evolves from the concept of application layer framing, ALF, and the let's wait session, LWS. The goal of SRM is simple, is that all receivers eventually receive the complete data. So the design attempts to follow the core design principles as TCP/IP. First, they require only the basic IP delivery model, which is the best effort services, with possible duplication and reordering of packets. In other words, a certain level of duplication is allowed in this model, and it tries to build the reliability on an end-to-end basis. no change or special support is required from the underlying IP network. Second, in a fashion similar to TCP, adaptively setting the timers or congestion control windows. The algorithm is proposed in SRM dynamically adjust their control parameters based on the observed performance within a session. This allows the applications using this model to adapt to a wide range of group size, topologies, and link bandwidths while maintaining robust and high performance. However, if a TCP-style sender-based approach is applied to multicast distribution, a number of problems occurs. First, because the data packet triggers acknowledgement, the ACK, from all receivers, the sender is subject to the ACK implosion effect. Second, since the IP multicast model deliberately imposes a level of indirection between senders and receivers. In other words, the data is sent to the multicast group, not to the set of receivers. The receivers set may be expensive or impossible to obtain. Finally, the algorithms that are used to adapt to changing network conditions tend to lose their meaning in the case of multicast. For example, how should the round-trip time estimate for retransmit timer to be computed when there may be several orders of magnitude difference in propagation delay to different receivers? So these problems illustrate that a single point sender-based reliable control is not adapted to or scale well for multicast delivery. Therefore, the receiver-based reliability is used in this SRM strategy. Here, we move to the SRM framework. SRM was initially designed for the whiteboard, and it's prototyped as this application called Whiteboard, WB. It adopts the receiver reliable mechanism. So the NACK is sent out based on retransmission, and every member may multicast the NACK message for retransmission request. So how to deal with the NACK implosion in SRM? Here, we provide two pictures to show how SRM work in a nutshell. Each time the packet is sent out to the receivers, R1, R2, and R3, each receiver will set up a timer, but with different intervals, because the distance between the sender and the receiver are different. Therefore, the timer length will be different. It varies by the distance between the receiver and the sender. In this case, the R1, which is physically closer to the sender side, it has a shorter timer. So once the timer in R1 expires, it sends out this retransmit request message, the NACK, to the whole multicast group, including the source and the receivers. Therefore, the R2 and R3 may receive this NACK before its timer expires. In this case, R2 and R3 will not be sending this NACK to the sender or the whole group anymore. In this case, and therefore the duplicated messages will be reduced. And once the sender or the other receivers who has this packets receive this request, the NACK request, it will send this packets, the targeted packets, to the multicast group. For example, here the sender received this NACK and resend this packet number 1 to the whole group. And the R2 and R3 no longer have to request to resent before the timer expires, and the packets will be successfully received by the whole group. So after understanding how the SRM works in a nutshell, let's see how the timers are set in SRM. So when a host detects a loss, it schedules a repair request for time in the future. As this request timer expires, the request is multicast to the group and the timer is doubled to wait for the repair reply. And the wait time is a function of the member's estimated distance to the source of the lost packets, which is the DSA here. The length of the timer will be chosen from this uniform distribution with this interval. If a host receives a request for the missing data before its request timer expires, for example, R2 receives the request from R1, then it does an exponential backoff. So the timer in R2 will be extended. The timer in R2 will be backed off to the power of I plus 1, which means it's doubled. And if a host B receives a request from host A, it sets a repair time to value from the uniform distribution, which means the host B has these packets that A is looking for. This function in the same manner as the request function. However, there is no exponential backoff if it sees another reply. It just cancels the timer. This is a uniform distribution of the repair timer. For example, host B received this request from host A, and luckily it has the packets that host A is looking for. It set up this repair timer and wait for the timer to expire. After the timer expires, it sends out this request, the targeted packets to host A. If the host receives the same packets that is requested by host A, it just cancels this timer. In this way, there will not be duplicated repair message in the network. Next, let me show some examples, real examples in different topology of applying this SRM strategy. First, it's the line topology. As we can see from this figure here, the topology of this network is in a line. So the data from this blue node is the sender, and the rest of them are the receivers. And when the collision happens, so in this figure, we can see that because the link between these two nodes are collided, so this node here will not receive these packets. And according to the SRM, the timer is chosen, the length of the timer is chosen from a uniform distribution based on the distance between itself and the sender. So in this case, the timer is chosen as 3D, and this node here will set up this timer as 4D because the distance between itself and the sender is 4D. And after 3D, the timer expires and this node did not receive the packet, it will send out this NACK message to the multicast group. And meanwhile, the receiver, this receiver, because the length of the timer is 4D, it did not expire yet. So it will not send this NACK message. but this receiver sends this NACK message to the whole group. So the receiver here also learns that this node did not receive the packets. So the timer here will be doubled. But at the same time, because this node and this node has the same distance, so the right node here receive this CK message, and it will set up this repair timer. After the repair timer expires, it will send out the repair packets to the multicast group. In this case, the green requester will receive the requested packets after this length of time. Also, this node here will receive the requested message after the same length of delay. Another example is the star topology. Also, the feature of the star topology, all the receivers will detect the loss at the same time. In this case, all the receivers will send out this NACK message to the multicast group simultaneously, because the delay and the distance are all the same. And each of the receiver will send this retransmit request to the whole multicast group. And in this case, only the sender has the targeted packet, which is the packet 1. When it receives this retransmit request, it sends out this packets again to the whole multicast group. And for this star topology, setting the request timer as a function of the distance from the source is not an essential feature, as all nodes detect a loss at exactly the same time. Instead, the essential feature of the request repair algorithm in a star topology is a randomized use the reduced implosion. We call this, the paper called this the probabilistic suppression. And the details of this probabilistic suppression is introduced in the paper. So if you are interested, you can take a look in this paper to see how this message could be suppressed in the SRM strategy. Conclusions. A brief summary of SRM. Here I listed several features of SRM strategy. First, the first type is the NACK retransmission suppression. So in order to suppress the number of messages exchanged between among the multicast groups, the delay before sending is used, which means each time when the sender or the host who has the targeted packets set up a timer before it sends out the to be retransmitted packets. In this case, if the same packets is received as this sender or the host will not need to send out the same packets again to the whole multicast group. Second, the delay based on round trip time estimation. The timer is the length of the timer is belongs to a uniform distribution based on the round trip time estimation calculated by each receiver, which has something to do with the distance between the receiver and the sender. Third is the deterministic plus stochastic components. In SRM, there's a dynamic algorithm that combines both deterministic and stochastic components together, which reduces the delay which reduces the delay in retransmitting the packets. Second is the periodic session messages. And these periodic session messages helps the SRM to achieve this full reliability. And also, it helps to estimate the distance metrics among members. So in conclusion, the advantages of the SRM can be seen as first, this mechanism doesn't require that all session member keep all of the data so long as each data is available from at least one member. Second, ideally, a loss generates only one retransmit request and only one corresponding repair reply. The problems of SRM are also listed here. First, one single loss causes request to the whole group. Second, it did not achieve retransmit to specific hosts as we have introduced in the ideal multicast strategy. Third, it did not achieve only request the nearest responder. As in SRM, it requests the whole group for the retransmission. Thank you for your time. If you are interested in this paper, you are welcome to discuss with me and also take a look at the original paper, which is very interesting and hopefully will be helpful to your research later on. Thank you.